This video is brought to you by mywayteaching.com.
In this part, let us study about cells, EMF, internal resistance. Okay. See, a simple device to maintain a steady current in an electric circuit is the electrolytic cell. We know this, right? Basically, a cell has two electrodes. One is positive and the one is negative. As you can see in the figure, see, it has two electrodes, as you can see in this figure, positive as well as negative, and they are immersed in an electrolytic solution. This is the electrolytic solution. Dipped in the solution, the electrodes exchange charges with the electrolyte. So these electrodes, they exchange charges with this electrolyte. Okay. The positive electrode has a potential difference of V plus. Okay, between itself and electrolyte. Electrolyte solution immediately adjacent to it, marked A, as you can see in this figure. Between the electrolyte and this bit, the point which is adjacent to it, there is a potential difference of V plus, as you can see in this figure. Similarly, the negative electrode, it develops a negative potential of minus V minus relative to the electrolyte adjacent to it. You can see adjacent to this point B in this figure. When there is no current, the electrolyte has the same potential throughout, so that the potential difference between P and N is given by, when there is no current, it is given by V plus plus of V minus. So this difference we call it as EMF, or in other words it is called as electro-motive force. Okay, and it is denoted by E. V plus plus of V minus, which is greater than 0. So this electromotive force is actually a potential difference. It is not a force. This is a potential difference. Okay, and the name that is, we call it as EMF. It is used because of some historical reasons. It was given at a time when the phenomenon was not understood properly, when they used to believe that this is a force, not a potential difference. At that time this name was given. Now, to understand the significance of this EMF, let us consider a resistor R connected across the cell. As you can see in this figure, resistance R is connected across the cell, isn't it? A current I flows across R from C to D. So a steady current is maintained because current flows from. So here also, see, this is the simple representation of this. So here the current I flows from C to D, and a steady current is maintained because current flows from N to P through this electrolyte. So across the electrolyte, the same current flows through the electrolyte, but from N to P, whereas through R, it flows from P to N. See, the electrolyte through which a current flows has a finite resistance R. We call that resistance as internal resistance. That is the internal resistance of the electrolyte. Now consider the first situation when R is infinite. So first situation we are considering when R is infinite. Okay. When this R is infinite, so that when R infinite means I is equal to V by R will be equal to 0, where V is the potential difference between P and N. So we can write that potential difference as V is equal to potential difference between P and A first. Plus potential difference between A and B plus potential difference between B and N. Okay. This is equal to electromotive force, and this electromotive force is the potential difference between the positive and negative electrodes in an open circuit, which means when there is no current flowing through the cell. If however R is finite, I is not 0. So here we are considering R as infinite, but if R is finite, I is not 0. In that case, the potential difference between P and N is given by, if R is finite, then that potential difference is given by V plus of V minus I into R. This R is the internal resistance of the electrolyte. So we can write it as epsilon or electromotive force minus IR. So here the negative sign in the expression IR here for the potential difference between A and B. This is because the current I, it flows from B to A in the electrolyte. In practical calculations, when we take internal resistance of the cell in the circuit, it can be neglected when the current I is such that it is, if it is very much greater than EMF, if it is very much greater than in IR, then we can neglect that internal resistance. Okay. The actual values of the internal resistance of the cell, it varies from cell to cell, and this internal resistance of dry cells is much higher than the electrolytic cells. So it depends on the type of cell also, internal resistance. For this dry cells, it is much higher compared to this electrolytic cells. Okay. So here we also observe that since V is the potential difference across R, we have Ohm's law. That is V is equal to I into R. Then we can write IR is equal to epsilon minus IR, or I is equal to epsilon by R plus R. The maximum current that can be drawn from a cell is when R is equal to 0, and it is given by I max, which is equal to EMF by R. So however, in most cells, the maximum allowed current is much lower than this to prevent the permanent damage to the cell. Okay. Now let us study one important topic, charges in clouds. See, in olden days, lightning was considered as an atmospheric flash of supernatural origin, and even it was believed to be the great weapon of gods. But today, the phenomenon of lightning can be explained scientifically by elementary principles of physics, isn't it? Yes. And atmospheric electricity arises due to the separation of electric charges. In the ionosphere and even in the magnetosphere, strong electric current is generated from the solar terrestrial interaction. And in the lower atmosphere, the current is weaker and it is maintained by thunderstorm, if you consider the lower part of the atmosphere. And even there are ice particles in the clouds which glow, collide, fracture, break apart. The smaller particles, they acquire positive charge, and the larger ones, they acquire negative charge. These charged particles get separated by updrafts in the clouds and even due to the gravity, and the upper portion of this cloud, it becomes positively charged, and the middle, it becomes negatively charged, and that leads to some dipole structure. Positive and negative separated by a distance, obviously it forms a dipole. Sometimes a very weak positive charge is found near base of the cloud, and the ground, it is positively charged at the time of thunderstorm development. And also cosmic and radioactive radiations, they ionize the air into positive and negative ions, and that air, it becomes electrically conductive. So the separation of charges produce tremendous amount of electrical potential within the cloud as well as between the cloud and the ground. So this can eventually, it causes the lightning flash, and this lightning flash begins and thousands of amperes of current flows. So because of this, there will be millions of amounts of volts, and eventually that electrical resistance in that air also breaks down, and that causes this lightning as well as thunderstorm. And thousands of amperes of current also flows through the atmosphere, and the electric field, it will be in the order of 10 raised to 5 volt per meter electric field in that case. A lightning flash, it is composed of a series of strokes with an average of about 4, and the duration of each flash is about 30 seconds. So usually it is composed of series, but the duration of each stroke is about 30 seconds, but which causes a tremendous damage. So the average peak power per stroke is about 10 raised to 12 watts per stroke. The average power per stroke is 10 raised to 12 watts. So during fair weather, also there is charge in the atmosphere. The fair weather electric field arises due to the existence of a surface charge density at ground as well as an atmospheric conductivity, as well as due to the flow of current from the ionosphere to the Earth's surface, which is of the order of picoampere per square meter. And the surface charge density at ground is negative. The electric field is directed downward. So over land, the average electric field is about 120 volt per meter in land. this corresponds to a surface charge density of minus 1.2 into 10 raised to minus 9 coulomb per meter square. So over the entire Earth's surface, the total negative charge amounted to about 600 kc. An equal positive charge exists in the atmosphere. So this electric field is not noticeable in daily life because it is not noticed is that virtually everything including our bodies is conductor compared to air.